now we're going to look at what happens when we take the formula for our function f and multiply it by a constant. And this, of course, multiplies the y values on the graph by the constant c. So if c is bigger than 1, that's going to push those y values away from the x-axis by a factor of c, or it's going to stretch the graph vertically by a factor of c. And if c is between 0 and 1, then it's going to shrink the graph. It's going to draw it closer to the x-axis by a factor of c. So it's going to shrink the graph vertically by a factor of c. We'll look at this in action for the graph of y equals x cubed. So we take some points on the graph. And then we look at the graph of y equals 2 times x cubed, and you can see that for corresponding x values, this just simply doubles the value, the y value on the graph. It's 2, 16, and 54. And then if we were to multiply it by 1/2, you see that the y values just simply, the y values on the graph of y equals x cubed, just simply get cut in half. So it's minus 13.5 here, minus 4, minus 1 over 2, 0, 1 over 2, 4, and 13.5. And if we were to sketch these, well, we get our usual graph of x cubed, and we'll let so we get minus 3, minus 27, make that minus 10, minus 20. Again, we're just talking a very rough sketch here. Minus 2, minus 8, minus 1, minus 1, 0, 0, 1, 1, 2, 8, and 3, 27. So it's our basic graph y equals x cubed, and because obviously this should be smooth, but I haven't quite done a good job on the scaling, so that looks a little messy, but you get the idea. That should be y equals x cubed. And now when I multiply the y values by 2, it means the distance from the origin gets pushed away, gets multiplied by 2. So we have, on the graph of y equals 2x cubed, if 0, 0 is right there where it was before, because that's sitting on the x-axis, so there is no distance from the x-axis to get multiplied by 2. When x is 1, this gets pushed up to twice the distance from the origin to 2. And minus 1, minus 2 is on the graph. And for x equals 2, then the distance from the origin here gets multiplied by 2, so it now becomes 16. And when x is 3, the distance from the origin gets multiplied by 2, so it's way up here at 54. So this graph looks like this. For every y value, every point on the graph is twice the distance from the x-axis that the corresponding point on the graph of y equals x cubed is. So it's twice x cubed, the y value. And likewise, the y values here get pushed away from the x-axis to twice the distance. Again, this goes way down here. So this graph gets stretched away from the x-axis by a factor of 2. Now, on the other hand, the points in this graph, their y values are just half the distance from the x-axis of those, the corresponding points in the original graph y equals x cubed. So we have the point 0, 0 because half of nothing is nothing. We have the point 1, 1/2, which is half the distance from the x-axis of the point 1, 1, 1, pardon me. And we have the point 2, 4, which is half the distance from the x-axis of the point 2, 8 on the graph of y equals x cubed. 3, 13.5 should be about here. You see that's the right half of the graph there. Could use symmetry. Just again take half the distance, this graph, from the x-axis. And so this is the graph of y equals 1/2 x cubed. And as before, you should try the next 3 problems, which are now going to require a combination of techniques to graph them, and see what you get, and then have a look at the next video to see the solutions.